Jack Jackson. We're getting ready to start looking more seriously at antiderivative and definite integral problems using these basic rules that we have just worked through in the previous video. Now basically we're going to have three types of problems that we're going to consider. The first of these is where we find a family of antiderivatives. This is also known as antidifferentiation, and it's also known as an indefinite integral. So for example, when you see this symbol like this with the integral sign without any limits, that means it's an indefinite integral or antiderivative, and it's asking you to find not one but the entire family of antiderivatives. At least that's usually the context that we use that notation. So here we can use the power rule by raising the power up by 1, dividing by the new power, and then we always have this plus c. So notice what we end up with is a formula for our answer where c is any real constant, and what this turns out to be is an entire family of antiderivatives. So it's an entire set of formulas for functions, and all these formulas differ by some constant amount. In other words, their graphs will be vertical shifts of each other. But notice that this gives you an entire family of formulas for functions, each of whose derivative is the original function that we have right here, what's called the integram. Now we may be also looking for a specific antiderivative. Now to do that, we need to be given an initial condition. We need more information to be able to narrow down or just isolate exactly what that value of c is. So what we'll be given is called an initial condition, and that's where we're given 1 point on the graph of that function, or 1 point in the table, 1 point that satisfies that. So we need an input-output pair that's known. So for example, we're looking for a function such that its derivative, so we're looking for the function g, okay, such that its derivative is x cubed, and we're given that g of 2 equals 5. So as we've seen above, the family of antiderivatives is 1/4 x to the 4th plus c for any c. Which c is going to work? We'll plug in 2 for x and 5 for y, and we can solve that. C to the 4th is 16, divided by 4 is 4. Subtract 4 from both sides, we see c equals 1. So the formula for g of x must be 1/4 times x to the 4th plus 1. Note that the answer to a problem of this type is a formula for a single specific function. Okay, a little different, not much different, but a little bit different than the first type of problem. And finally, we can have the problem where we find a definite integral. We want to find the exact value of this, and the function should be continuous on the interval that we're looking at to use the fundamental theorem of calculus. And so, for example, if we're going to integrate from 0 to 1 x cubed dx, we find any antiderivative, choose any c we want, like 0, and take an antiderivative like 1/4 x to the 4th here, and evaluate it from 0 to 1, which means take this, plug in the top number, minus, take this formula, plug in the bottom number, and see what we get. Of course, 0 to the 4th is 0, times 1/4 is 0, subtracting 0 doesn't change anything here. 1 to the 4th is 1, times 1/4 is 1/4, so when you work all the arithmetic out here, you get 1/4 for the answer. So note that the answer to this type of problem is actually just a number, a constant real number. Okay. Now, of course, that number has a geometric meaning in terms of the graph. Like, for example, we know it's the area under the curve from 0 to 1, under the curve y equals x cubed, and above the x-axis between x equals 0 and x equals 1. That bounded region there has an area of 1/4. And in the context of a real-world problem, this probably has some physical interpretation as well. But ultimately, it is just a number. But notice that in all three of these types of formulas, one we got a family of antiderivatives, one we got a specific formula for an antiderivative, and then one we got just a number. But the main step in all of these was really finding an antiderivative. And of course, that because of its close relationship to the definite integral, we end up using a very similar notation for this process of finding an antiderivative. And it's traditional to use the word integration to talk about any of these three types of problems. So in our next video, we're going to start working through some examples And the way we're going to do this is I'm going to basically start with a function, and I'm going to take that function and we're going to find a family of antiderivatives for that function, and then I'm going to give you an initial condition, and we're going to find a specific antiderivative that for that particular function with that initial condition. And then I'm also going to give you some limits, and we're going to find the definite integral of that function over that specific interval. So come back to the next video and we'll start putting this to work in some more examples.